remember our original definition of a rational function? It's the ratio of two polynomial functions that don't have a factor in common. So now, if the numerator and denominator have a zero or a factor in common, there will be a hole in the function's graph. And all a hole looks like is on one of your elbows, you'll just have a little open circle to show that it's undefined at that one particular point. So to graph the function, you first have to factor the numerator and denominator to discover if there are any common factors. And then you find the hole by evaluating the new function created by canceling the common factor. So I'll show you what to do with that in a minute. All right, so it says find the new function to be graphed and its hole. And I'm going to start with example 2 because it's already in factored form for us. Do you see any common factors? X minus 2 is exactly the same. So I'm going to cancel out the factor x minus 2. And I'm just going to rewrite that the new function is 3 times x minus 5 over x plus 1. And if you want to distribute the 3, you can, but sometimes it's easier to leave it in factored form. So we're going to practice every step that we normally do, the y-intercept, the x-intercept, the vertical asymptote, the horizontal or slant asymptote, and then step 5 that we're going to add to our note card after we do this is going to be the hole. So to do the y-intercept, I'll do this one with you, and then maybe after we do our kind of a third example together, then you can start finding these 4 pieces using your own note card. But the y-intercept, when I plug in 0 for x, I get negative 15 in the numerator and positive 1 in the denominator. So negative 15 divided by 1. My y-intercept is at negative 15. So that's kind of off the graph, but I'm just going to put a dot to show that it would be way down there on the axis. Because it's going to still show you where your elbow is. All right, my x-intercept. So I look only in the numerator. What would make that factor equal 0 when x is positive 5, right? Because 5 minus 5 would give me 0. So my x-intercept is at 1, 2, 3, 4, 5 on the x-axis. So that I can kind of see that elbow taking place. What would make the denominator undefined when x is negative 1? So that's my vertical asymptote. X equals negative 1, vertical line. So I can see that that elbow is going to run down parallel to that vertical asymptote. All right, and then for my horizontal or slant asymptote, I compare the numerator, linear function, with the denominator, also a linear function. So I'm going to strip the coefficients of x. This 3 is actually in front of this x. So this is 3x divided by 1x. So y equals 3 is going to be my horizontal asymptote, 3x over 1x. So 3. So I'm going to draw my elbows like I normally would, and then I'm going to show where my hole would be. Let's see, I need to plug in a value to the left. So like when x is negative 2, I think I'm going to be in this top left region. But if I plug in negative 2, I would get negative 7 times 3 is negative 21. And then I'm plugging in negative 2, so I would get negative 1 in the denominator. So positive 21, so that's way up here off the graph. So I do know that my elbow runs through this region because I was at negative 2, positive 21. All right, so this hole. This function looks exactly like this. So the only difference between the original function and our new function is this factor of x minus 2. Where should this have had a vertical asymptote? Originally, it should have been undefined when x was 2, right? So at 2, wherever it is on here, there needs to be a hole. So I take 2 and I plug it into this function and I evaluate this at 2. So I would do 3 times, this would be negative 3. So 3 times negative 3 is negative 9. And then if I plug in 2 in the denominator, I would have 3. So negative 9 divided by 3 is negative 3. So my hole is at positive 2 comma negative 3, which my elbow almost went past that point. So just kind of adjust your elbow so it touches 2 comma negative 3. That's a hole, open circle. So if I graph this on the calculator, you won't see any difference between the two functions. So if I graph my original function, 3 times x minus 2 times x minus 5 divided by x minus 2 times, I got to put a lot of parentheses, x plus 1. So there's my original function. My new function was 3 times x minus 5 divided by x plus 1. So if I graph these, hopefully I typed them in right. So the blue is the original function, and then the red is the new function. So on the physical graph, you can't see any difference. The only place that you're going to see the difference is in the table. So if I go to the table, where did we say the hole was at? 2, right? So see how at positive 2, whoops, the original function, because that factor was sitting in the denominator, had an error. So it has a hole at that point. Because I typed in this new function and that factor is now gone, you don't see the difference in the table. So where was our asymptote? Our asymptote was at -1. So if I go to -1, there's an error for both because that's still an asymptote, but this just has a hole because we got rid of that factor in the denominator. So this is just showing us that, hey, this represents that that factor really was a part of the original function. But all the other steps are the same. All right, so let's do one together where you actually have to factor. This is where your factoring skills are important. I can't start answering all my questions until I create my new function. So the numerator, you're going to use the diamond method. The denominator, you're going to use greatest common factors. And there should be something that you're able to cancel. So why don't you take a stab at factoring it yourself for just a minute, and then I'll put it up if you can't get it. So how did we do? The numerator factors into x minus 2, x plus 1, right? Because you're looking for the factors of -2 that add up to -1. And then the denominator, you can factor out the greatest common factor of x. So we end up canceling x minus 2 as a factor, and we only look at this new function when we're figuring out all of our things, our y-intercept, our x-intercept. So if you forget to factor, it's going to like mess up some of your answers. So you want to start with your new function, find your y-intercept, x-intercept, vertical asymptote, and then horizontal or slant asymptote, and then at the end, we'll do the whole. So why don't you try the first 4 steps? I'll give you like 3 minutes. See if you can get your intercepts and asymptotes. They're pretty straightforward because you're already in factor in the top right because there's no other x-intercept, but a good value to plug in would be like +1. So if I plug in 1, I would get 2 divided by 1, which is 2. So 1 comma 2 lies on this elbow up in the top right. 1 comma 2. All right, so your whole, you look back to your canceled out function and you think about what your asymptote should have been. You should have had an asymptote at 2 because 2 minus 2 should have given you 0 in the denominator. So 2 is the x value of your whole. And if you tried to plug it in your original function, it would just be undefined. You have to plug it into your new function to see what your output will be. So when you plug in 2, you get 3 divided by 2. So 3 halves or 1.5, and that should actually fit right on your graph. So at 2, you're at 1.5. So there should be an open circle, just kind of estimate, but that's at 1.5. 2 comma 1.5. If your elbow doesn't go through your hole, Either your elbow is wrong or your hole is wrong. It should sync up right on your graph. It's another way to check that you've got your elbows in the correct spot. All right, let's do another one together. So I want to show you the cheater method for factoring. If you suspect that there is a canceled out factor, what is the only factor in the numerator? 2x minus 1. So guess what? I bet 2x minus 1 will show up in the denominator. See, there's a little workaround sometimes for factoring, because now all you have to do is make up the second factor that's going to work for you. So 2x times what will give you 2x squared. You know the first term needs to be x. And then for your last term, you've got a negative 1 times what will give you this positive 3. It would have to be negative 3 to make it true. Then you can just double check. Does your outer plus your inner add up to the negative 7x? It does. Negative 6x, negative 1x is negative 7x. So you don't have to go through the whole box method on some of these. If you kind of use that cheater strategy that I'm trying to cancel something out, it has to show up in the denominator if it's going to cancel out. It won't always work because there won't always be a hole, but it's a good little cheater method for rational functions. So your new function is 1 over x minus 3. There is a 1 in the numerator because anything divided by itself is 1, not 0. So we're going to go through this new function, find the y-intercept, the x-intercept, vertical, horizontal, and whole. So now that it's in the correct format, why don't you try going through those steps for a couple minutes on your own and graphing it and see where you get stuck. And if you get the whole thing done, move on to number 4, try factoring it on your own. I'll walk around for a minute. Answers to, let's see. So your y-intercept should have been at negative 1/3, right? 0, negative 1/3 is right here. That is your x-intercept. So your x-intercept, you look at the numerator, right? That can never be 0, so that's why there's no x-intercept. But if you want to plug in 0, then there would still be a 1 in the numerator and a negative 3 in the denominator. So I think that you just flip-flop those in your head. But negative 1/3 is your y-intercept. There's no x-intercept. The vertical asymptote would be at positive 3. So x equals 3 is your vertical asymptote. And then we haven't done this one yet today, but our denominator is bigger because you've got a constant function and a linear function, so the denominator wins. When the denominator wins, it's automatically horizontal asymptote at y equals 0, and that makes sense because we did not have any x-intercepts. So those kind of go hand in hand. So I have no x-intercept because I've got an asymptote there. So I can see where this elbow is reaching. The other elbow is probably in the top right, just because they're usually opposite each other, but I should plug in a value. This was at positive 3, so I should plug in positive 4. So when I plug in positive 4, I just get 1 over 1, right? So 4 comma 1 is the point on my other elbow. Now I need to determine the whole. So I look back to the original denominator that I had canceled out. There should have been an asymptote where 2x minus 1 equaled 0. So if I set that factor equal to 0, I would add 1 to the other side and divide by 2. So x should have been undefined at 1/2. So my whole is at 1/2. So this is one that I probably wouldn't have you calculate without a calculator, because now you need to plug in 1/2 up here. So it would be 1 divided by negative 2.5. So what is 1 divided by negative 2.5 is negative 0.4. So that wouldn't be one that I would have you calculate by hand. But so at 1/2, it looks like, yep, at 1/2, I would be at negative 0.4. It's kind of hard to squeeze on your graph, but it'd be right there on that elbow. My y-intercept, and then right after my y-intercept, there's a hole on that graph. I'm going to have you record the coordinates of the hole, so if the graph isn't perfect, I can just see what your hole should have been at. So I wrote, so on the back, you're going to write step 5, find the hole if there is a common factor. So here's my example. X plus 2, x minus 1 over x plus 5, x minus 1. So you cancel the factors. This is your original function, and this is your new function, x plus 2 over x plus 5. So to find your hole, you plug in the undefined value into the new function. So my undefined value was 1. So I'm going to take 1 and plug it into this function. So I would get 1 plus 2 over 1 plus 5 is 3/6. So my hole would be at 1 comma 1/2. We'll actually have no hole because the factor that you canceled is the same as the factor of your asymptote. You can't have an asymptote and a hole. So you won't have any hole because the same factor is still taking precedence as an asymptote. So go ahead and try your steps 1 through 4, and you do not have to do a hole because what you canceled is still sitting in the denominator. So see if you can finish that one with your steps, but no hole. For the sake of my video and time, put it up. Let's see. Y-intercept, -10, 6. -10, 6 is less than 2, right? X-intercept is at 2. Vertical asymptote at -2. Horizontal asymptote at 5/3. Strip the coefficients of the numerator and denominator, so that's just more than 1, but less than 2. So elbow, I guess the tricky part maybe was the -10 sixth. When you plug in 0, you get -10 over 6. Let's see, I have to plug in -3. So if I plug in -3, I have 5 times -5 is -25. And if I plug in -3, I would have -1 times 3 is -3. So it's going to be somewhere high positive, right? 3 times 8 is 24. So is it 8 and a 8 point something? Yeah, 8 1/3. So I'm somewhere up here. So at -3, I'm at positive 8 1/3. This one, I don't know, because of the fractions, I probably wouldn't give you one like that without a calculator, but some of the steps weren't too bad. This was a little bit more challenging to factor, and it was a little bit challenging to know that there was no hole. So, you know, number 4 was definitely a more challenging problem. I would probably gear towards examples like 1 or 2 for your quiz, and then maybe an example like number 3 for your test, factoring with like the box method.